Hello, my name is Jennifer Campbell, and today I'm going to talk about the aggregate G-ratio weighted imaging framework and beyond. I'll spend the bulk of the talk discussing tissue models and the imaging frameworks that go with them to estimate the G-ratio from MRI, starting with what we call the voxel fraction-based framework, and then moving on to alternate frameworks. I'll then talk about some future directions to go beyond the voxel aggregate G-ratio, in particular in order to estimate a G-ratio for each of multiple fiber populations in the voxel. Throughout, I will discuss challenges, but I will summarize these challenges at the end. Here we have a scanning electron micrograph of white matter. And here it's been segmented into different tissue compartments. The blue is the interaxonal space. The red is the myelin sheath, and we'll call the rest extraaxonal space. So from this, we can start with a simple tissue model that has these three compartments in it. As we've seen already, the G-ratio is the ratio of the inner to the outer diameter or radius of the myelin sheath. And as Thomas Kanija discussed in the previous talk in this symposium, it is the key determinant of conduction velocity and therefore of function. To date, there have been a couple of studies using the MR estimated G-ratio in the context of conduction velocity. There have also been a number of other studies in healthy white matter, including looking at development and aging. G-ratio imaging has also been explored in pathology, for example, in multiple sclerosis. And just to motivate why we want to measure this parameter, on the left, we have healthy white matter, the tissue model that I introduced already. And in MS, traditionally, myelin-sensitive MRI metrics have been studied. But the total myelination in a voxel can change for different ways. For example, we could have some axon loss with the remaining axons experiencing demyelination and partial remyelination. Or we could have more severe axon loss with the remaining axons having a relatively healthy G-ratio. And so the G-ratio allows us to decouple the total fiber volume fraction from the relative myelin thickness, which is the G-ratio. So now I'll describe what we call the volume fraction-based framework for estimating a G-ratio. Here's our tissue model again with the myelin volume fraction, axon volume fraction, and the sum of these two would be the fiber volume fraction. Nicholas Stikov showed that for the aggregate in the voxel, the G-ratio can be expressed as a function of any two of these three parameters. And so here you see it expressed as a function of the myelin volume fraction and the axon volume fraction. And the G-ratio is determined entirely by the ratio of these two quantities. Alternately, we can express it as a function of the myelin volume fraction and the fiber volume fraction. And again, it's determined entirely by the ratio. So if we want to estimate a G-ratio weighted image, one possibility is to estimate volume fraction weighted images first and then compute the G-ratio. So I'll start with the myelin volume fraction. The myelin compartment in this tissue model consists of myelin water and macromolecules, and there are a number of different MRI contrasts that are sensitive to the myelin in different ways. So if we assume this tissue model is complete and the myelin marker is specific, let's call the myelin marker M, then we can estimate myelin volume fraction as an appropriately scaled version of M. Now, Siawish Mohammadi later in this symposium will talk about what happens when this relationship does not hold. For the time being, I won't say anything more about that, but one should be careful that it is an appropriate approximation. So from this, we can make a map of the myelin volume fraction, and we can plug this into the G-ratio formula here, as seen in the second equation here. So now we need to estimate the fiber volume fraction. There are a couple of possibilities. One is diffusion imaging, which would be sensitive to the fiber volume fraction because the diffusion displacement distributions in the different compartments are distinct. Another is the complex multi-echo GRE signal, where the phases of the different compartments would be distinct. So what Nicholas Stikov originally did was he did simulations in straight parallel fibers of the diffusion of water molecules, and he determined that the fractional anisotropy of the diffusion tensor had a quadratic relationship with the fiber volume fraction. So taking that relationship into the G ratio formulation, here we have it here. Now, the diffusion tensor is a signal model, and the FA would be expected to be dependent on the diffusion acquisition parameters. And furthermore, it would be very dependent on the axon geometry. So we asked whether we could go beyond this straight parallel fiber assumption. And to do that, we switched to the formulation for the G ratio that uses the axon volume fraction here. And we asked whether we could use diffusion modeling to estimate the axon volume fraction. So before we get on to that, I just want to point out that both of the myelin compartments have a very short T2. And so in a typical diffusion acquisition, we would get negligible signal from the myelin compartment. So when we do compartment size modeling using diffusion imaging, we're looking at the other compartments. And the diffusion imaging will give us a signal fraction of what I'll call the intraneurite space here. Now, what we originally did was propose to use the intraneurite signal fraction directly in the G ratio formulation. I'll get to problems with that in a moment. And because we get no signal from the myelin, we need to adjust this fraction using our myelin volume fraction that we already computed. And this will give us a relationship that we can use for the G ratio. However, a number of recent studies using multiple TE diffusion acquisitions have shown that the T2 of the interaxonal and extraaxonal spaces are quite different. And they may be regionally variable. And if we look at pathology, the polarity of the difference between the interaxonal and extraaxonal T2s may switch. And so just to show you what's happening, if we want a fraction that is independent of relaxation, here, let's say the intraaxonal and extraaxonal fractions are actually the same. It's this F0 I'm showing here. When we do our diffusion modeling, what we're getting is the signal fraction here. So they look very different, and as the relative T2s change, the difference between them will change. So we really need to correct our signal fraction for relaxation to get a signal fraction that is independent of relaxation. If we do that, then this becomes the formulation for the G ratio. So now we need to consider some other compartments in our model. If we have free water, by which I mean water that's not significantly hindered or restricted diffusion-wise, such as cerebrospinal fluid that may be partial volume averaged with our tissue, then diffusion imaging can also give us a signal fraction, often called the ISO signal fraction for that free water. And it would be expected to have very different relaxation times from the rest of the tissue. So we should also correct it for relaxation, where again, this F0 is the signal at T equals 0 and TR sufficiently long for complete longitudinal relaxation. And so if we correct all of our fractions for relaxation, this is the formula for the G ratio. Now we need to consider a few other things. There may be non-myelin macromolecular content in the extraaxonal space. So when we adjusted the axon volume fraction that we originally got from diffusion for this invisible myelin compartment, we really needed to include this extraaxonal volume fraction that is not myelin as well. Once we do this, it is ongoing work how we would differentiate these with MRI. But if we can do so, this is the formulation for the G ratio. But we're not done yet. There may be interaxonal non-myelin macromolecules as well. So what I propose is that we correct all of the signal fractions that we get from the diffusion modeling for the non-myelin macromolecular content as well. And the literature has estimates of what this may be in healthy tissue, but I think it's ongoing work to figure out what it would be in pathology. So now I'm going to move on to alternate frameworks for estimating the G ratio from MRI. There is a model called the hollow cylinder fiber model that expresses the myelin-induced frequency offsets of the myelin interaxonal and extraaxonal spaces directly as a function of the G ratio. So what Mark Drakesmith did here was in the mid-sagittal corpus callosum, he employed this model with multi-echo GRE data to estimate the G ratio. We can take this a step further. If we use a long TE to make the myelin signal negligible, and we prepend a phase-sensitive acquisition with high diffusion weighting that would knock out the extraaxonal space, we're left with just this middle equation. And that's what Mikhail Katar has done with his diffusion-prepared phase imaging. And he can estimate a G ratio from this. And I'll come back to this in a little bit. But we can take the hollow cylinder fiber model a little further and replace it with more realistic axonal packing geometries. And this is what Jose Marques will talk about more in the symposium, but he's used a machine learning approach to estimate the G ratio and fiber volume fraction from GRE data using more realistic axon geometry models. Another approach that you might have thought about when I mentioned that the fiber volume fraction is related to the fractional anisotropy of the diffusion tensor is that the diffusion data, your diffusion acquisition, despite having negligible signal from the myelin compartment, is sensitive to the myelin compartment in that the extraaxonal diffusion anisotropy depends on the amount of myelination. And so this has been formulated by Bjorn Lampinen here. And here, this is the stick fraction, which I've been calling the intraneurite volume fraction. It is the anisotropically restricted fraction where he has corrected for relaxation. And so he can compute the G ratio directly from diffusion data alone. So now I'll talk about future directions in estimation of the G ratio for multiple fiber populations in a voxel. So when I talked about the diffusion prepared phase imaging of Mikhail Katar's work, in fact, this approach allows for the estimation of a G ratio for multiple crossing fiber populations that are oriented at different angles to the main magnetic field in the voxel. So this was showing simulations of two fiber populations, and he's recently shown in vivo results where he's, well, showing the average G ratio along a tract where when he averaged, he chose the G ratio of the fiber orientation that lies along that tract. If we go back to the volume fraction-based approach, we would need to estimate volume fractions for each of the crossing fiber populations. I'll start with the myelin volume fraction. A number of groups have looked recently at combining diffusion imaging with sensitization in the same sequence to a myelin sensitive parameter such as T1, which has been done using inversion preparation or multiple TRs. And this is showing an example of the T1 along each fiber population using inversion prepared diffusion imaging. Another approach is called commit, which allows for the estimation of an MRI parameter along a streamline or bundle with the assumption that it is constant along that streamline or bundle. So this shows bundle-specific myelin water fraction, magnetization transfer saturation, and magnetization transfer ratio. And what Simona Schiavi has proposed is that we also use commit to estimate a streamline-wise interaxonal volume fraction, and then combine the streamline-wise interaxonal volume fraction with the with the myelin volume fraction to compute a streamline-specific G ratio. And then we can map this back to the voxel level, and we'll have a G ratio for each fiber population in that voxel, if they're crossing, or even if they're not, provided they then diverge in the rest of the brain. So now I'll summarize some of these challenges that we've talked about and some that we have not talked about. We really need to pay attention to relaxation if we're going to correct our signal fractions to be closer to volume fractions, which we need for such a geometric model. And we also need to pay attention to non-myelin macromolecular content that's not visible in the diffusion acquisitions to get closer to the volume fractions. It would be nice to estimate a G-ratio distribution as opposed to a voxel aggregate. We haven't talked a lot about specificity and accuracy of myelin markers, but Siawish Mohammadi will talk more about that. And I didn't get to talk a lot about remaining challenges in diffusion modeling that are ongoing work in the field, such as dealing with degeneracy of output parameters and exchange. Another open question is applicability in gray matter, and more validation is needed, and some has been done, and I haven't talked a lot about that, but I welcome you to talk about any of these topics during our panel discussion or talk to me about them after. So in summary, G-ratio weighted imaging is a way to interpret MRI data that are sensitive to myelination and axonal volume. G-ratio weighted imaging is limited by the specificity and accuracy of these MRI metrics. And recent methodological advances have taken us closer to estimating more than one G-ratio per voxel. Thank you for your attention, and I hope we'll have a nice discussion after these talks.